Welcome to this video lecture series on antenna and wave propagation. In this video lecture, we'll discuss the feed methods of reflector antenna. So we'll begin. So the first feed method is using dipole antenna. So I know a dipole antenna looks like this, and the radiation pattern of dipole antenna has two maxima, in this direction and in this direction. So when the radiations comes here, it gets reflected and it comes again in this direction, but it gets hindered by this radiation as well. So now the second method is using dipole and secondary reflector. So here I have my dipole. The dipole produces radiations. These radiations would encounter another parabolic reflector, and this parabolic reflector reflects the waves which encounter one main parabolic reflector, which then reflects the wave, and the waves came into this direction. So the third method is using unidirectional antenna. So here I was using my thin linear dipole antenna. So in thin linear antenna, I have radiations in this direction and in this direction. So when reflected waves come back, these are hindered by this radiations as well. So to avoid this condition, I'll use unidirectional antenna. So unidirectional antenna are Yagi-Uda antenna and horn antenna. So these are producing radiations in one direction only. So this method is better than this method. So second type of feed method is Cassegrain feed method. So in Cassegrain feed method, I am using a parabolic reflector and a hyperbolic reflector and a horn antenna. So horn antenna would reflect and the hyperbolic antenna would again reflect, which will come here. So now it has various advantages. So it has advantage that it can place feed antenna anywhere. So I can place my feed antenna anywhere in this configuration, but in all of these configuration my feed antenna was placed at the focus only. So now the offset paraboloid antenna. In offset paraboloid antenna, I'll place my antenna downside the main antenna and the reflection would occur like this. It has advantage that no hindrance is produced and disadvantage that cross polarization is produced. I know that the parabolic reflector is making the spherical waves into planar waves. So after reflecting from the parabolic antenna, my spherical waves turns into the planar waves. So now we'll see the patterns of large circular aperture with uniform illumination. So we have three cases in this. So first case is when focal length is less than d/4. Here d is the length of the aperture. So at this case, I have less efficiency and less gain, because my object is placed very near to the antenna. So in this case, my focal length is greater than d/4. Here all of the rays might not reach to the reflector and some rays get diverted. So here I get some rays which are diverted and the efficiency is again less. So this is the ideal condition when focal length is equal to d/4. So I'll see various properties related to this from Huygens principle. I know that E phi is equal to 2 lambda upon pi d, first Bessel function, pi d upon lambda sin phi upon sin phi. So when I need to calculate first null beam width, I know that E phi should be 0. So my first order Bessel function should be 0, which occurs at 3.83. So my pi d upon lambda sin phi is equal to 3.83, which implies phi is equal to 1.22 upon d lambda, where d lambda is equal to d upon lambda. So here are various parameters for half power beam width, first null beam width, directivity and power gain. So for aperture antenna and for rectangular antenna, half power beam width is equal to 70 upon d lambda. For rectangular it is 51 upon L lambda. First null beam width is equal to 140 upon d lambda. For rectangular it is 115 upon L lambda. Directivity is equal to 9.9 d lambda square, 1.26 L lambda into L lambda dash square. Power gain is equal to 6 d lambda square. Here it is 7.7 L lambda multiplied by L lambda dash square. So here I'll conclude this session. I hope you like this video. Like this video, subscribe this channel and stay tuned for the further videos. Thank you.